All right, welcome back. Today is exciting because we take the leap into infinity. We will be talking about infinite series in general, and our first particular class of infinite series that we will study called geometric series. But as a little motivation for getting towards infinity and to connect it to what we've done already, first I want to talk about extending Taylor polynomials to so-called Taylor series, where the polynomials have infinite degree.
Okay, I am back with the graph of cosine. Now, cosine is one of the four functions whose Taylor expansion at 0 you should already know by heart. You should know cosine, sine, e to the x, and 1 over 1 minus x. You found those in the very first homework problem. There are a few others that are nice to know, but those are the four that at this point you should know, like 2 times 3 is 6. If someone wakes you up in the middle of the night and says, quick, I need a 6th degree Taylor polynomial for cosine centered at 0, you should be able to mumble, after only a couple of seconds to collect your bearings, oh yeah, that's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And the pattern continues if you want to go further. And of course, this pattern is very easy to remember for a couple of reasons. First, it begins with 1. Of course it begins with 1 because the graph of cosine begins at 1. What's the other thing? All the terms are even. How do you remember that cosine has even powers? Because cosine is an even function. Anyway, I want to put one of its Taylor polynomials up on the screen. Let's start with the second degree. There it is. Already at the second degree, it looks like a really good approximation near 0. Pretty far out, in fact. Well past 1. But let's zoom in a bit where it looks like the approximation is pretty good, just to take a closer look. Let's get out the old magnifier glass and zoom in. That looks pretty good. And if you see along the bottom here, those are the x values. And for example, at 0.6, you can barely see any distinction at all between the two functions. But actually, that's just because of the scale we're on, where we just have things measured out by 0.1 on the y-axis. Let's zoom in even closer and see what we can. Oh, okay, now we can start to see the two resolve themselves. Here we are at 0.6, and we can see there actually is a distinction now that we have really fine distinctions on the y-axis as well. What if I put the 4th degree? Let's see. Ooh, you can barely see the 4th degree because it is right on top of the function. It looks like a perfect match. You cannot see any difference between the 4th degree Taylor polynomial and the original function, even when we're on this tiny scale. But let's see. Let me remove the 2nd degree, but let's keep zooming in here around 0.6, around x is 0.6. If we zoom in close enough, oops, I'm losing it. 0.6 is over here. Look at that. We can see them separate out. We've got a very small difference here. Our y-axis, we're measuring things now in, what is that, 2/10,000ths. Each one of those ticks is a 5,000th. But we can actually see a discrepancy between the cosine function and the 4th degree Taylor polynomial when x is 0.6. So maybe if we want a really good fit there, we just need to jack up the degree a little further. Like we'll go to the 6th degree. Or let's go crazy. Let's go to the 8th degree Taylor polynomial, which looks like this. And again, the 8th degree is so much better than the 4th that you can't even see a difference between the 8th degree Taylor polynomial and the cosine function on this scale. Let me get rid of the 4th degree Taylor polynomial, and let's zoom in even further. This is looking really close. Okay, man, I'm going to have to go. So, oh, look at that. It's starting to separate. Let me scooch this over a little more, and 6e to the minus 1, that's 0.6. We can actually see the discrepancy now between the cosine function and the 8th degree Taylor polynomial. It's a tiny difference, as you can see over here on the y-axis. But you get the point. I could do this all day. Don't worry, I won't. I could put up the 20th degree Taylor polynomial, and it would take a long time, but if we zoomed in close, eventually we would see a separation of the two. Because in fact, the curve and the Taylor polynomial of any degree are always slightly separate except at the actual anchor point where they coincide. But let me zoom all the way out again. All right, here we are again on a normal scale with that 8th degree Taylor polynomial still up. And down here is a reminder of how we've been thinking about these things, that cosine is approximately equal to that 8th degree Taylor polynomial, at least for x near 0, and in this case, quite some distance from 0 too. But as we've just seen, increasing the degree of the Taylor polynomial gives us a better and better and better and better fit. Well, what happens when we don't stop at the 6th degree, at the 8th degree, at the 20th degree, at the 42nd degree, whatever? What if we just keep going? In that case, the approximation becomes exact. Instead of this approximation for some particular degree, we now have equality. The cosine function, this geometrically defined function, is actually equal to that infinite degree polynomial. It's hard to get your head around that. That's not just some polynomial of very high degree. That's not a 100th degree polynomial. It's not a millionth degree polynomial. It's not a trillionth degree polynomial. It is an infinite degree polynomial. To signal the fact that this is a difference not of degree, but of kind, we don't even call it a Taylor polynomial anymore. We call it a Taylor series. And it is literally the same function as cosine. There is no small discrepancy anymore. Oh, and that little note about for x near 0. In this case, we can actually remove it. This function is equal to its Taylor series for all real numbers x. For other functions, we can't remove it. We'll talk about why later on, but this goes back to that mystery from the first lecture, where we saw functions like e to the x, where the Taylor polynomials hugged the functions over a larger and larger and larger region of the domain as we increase the degree of the Taylor polynomial, versus functions like 1 over 1 to the x, or 1 over 1 plus x squared, or cosecant. Those were all examples we looked at, where no matter how high we drove up the degree of the polynomial, it couldn't approximate the function outside of a certain small region. And I likened it to laser tripwires, that once the function passes through them, it destroys the ability of the Taylor polynomial to follow it. But those fine details we will get to in good time. For now, I just want to emphasize the idea of a Taylor series, which is that wherever those polynomials did approximate the function well, in the limit, as we go to an infinite degree polynomial, it's no longer an approximation. It becomes perfect. Those discrepancies we saw by zooming in no longer exist. The function and the Taylor series are literally the same, which is why we use an equals sign, not the squiggly approximately equal sign we used with the Taylor polynomials. Being able to think about familiar functions like cosine and e to the x in these unfamiliar ways as infinite degree polynomials, as Taylor series, will give us insights into those functions themselves that we never had before.
I'm going to give you a really hair-raising example that has to do with functions that should seem as familiar to you as anything: sine, cosine, and the exponential function. You've been working with these guys since pre-calculus. What else is there to say about them? Well, you'll see. Hang on to your hats. Let's begin by recalling the Taylor series for those three functions. Now, back in exercise 1 of the previous homework, you figured these things out. Granted, you learned them only as Taylor polynomials, but you saw the pattern, and that just continues to infinity. I already reminded you in this video of the Taylor expansion for cosine, this guy. Now let's move on to sine. Sine is odd, so this has only odd-powered terms. And finally, e to the x looks like this. It's hard to imagine functions more dissimilar than the trig functions and the exponential function. I mean, the exponential function just takes off and grows without bound. Even in common parlance, we use it to connote something with explosive growth. Sine and cosine are quite the opposite. They both just bobble along between -1 and 1. And they repeat themselves over and over and over and over again, totally unlike the exponential function. So it would be surprising to find any link between those functions. And yet, a link there is. As I suggested earlier in the video, there are some functions whose Taylor series only hold over some limited interval, like the Taylor series for 1 over 1 minus x, which only holds when x is between -1 and 1. But these three Taylor series, these series expansions hold for all real numbers. Even though these are all centered at 0, if I take the number 42 million and pop it in every one of these all the way down to infinity, what I will get out is sine of 42 million. In fact, the valid playing field for these functions is much wider than you suspected. Not only can you put any real numbers in there, you can put any complex numbers in there. We're not going to really be doing anything with those in this class, and you've probably only brushed briefly against complex numbers in the past, but I can't resist bringing them in this one place. Anyway, as I say, we can evaluate any of this stuff at complex numbers. That is, numbers of the form a plus bi, where I is the mysterious square root of -1. We're going to be raising I to powers, So let's take a moment and just recognize how we do that. It's actually very, very, very simple. Since I is defined to be the square root of -1, of course, I squared is -1. But that means I cubed is, well, that's I squared times I again, and this is I squared, so if we multiply it by I again, we're going to get minus I. And how about I to the 4th power? Well, that's I cubed times I again, and if we multiply I cubed, which is minus I, times I, we get minus I times I, but I times I is -1, so we get minus 1, which is just good old-fashioned 1. So among other things, I is a 4th root of 1. What about I to the 5th? That's like multiplying I to the 4th times I, so we get 1 times I, which means we're back here at I. So maybe I'll go ahead and write here in another color, I to the 5th is I. But that means that I to the 6th must be I squared, which is -1, and I to the 7th is I cubed, which is minus I, and I to the 8th is I to the 4th, and we're back around at 1, and you see what's going to happen. I to the 9th brings us back around. I to the 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, and so on and so forth. It's kind of reminiscent of the cycle of derivatives of sine, where you keep going around and around and around every 4. Already there's an interesting connection. What I want to do is take the exponential function and evaluate it at I theta. This is just some real number times I. God knows what this means, you might say. E to the I theta? What could it possibly mean? Well, I can reduce it to arithmetic because I have this Taylor series for it. Remember how I said Taylor stuff can turn things that are defined in weird ways into mere arithmetic? That works here too. If I pop I theta in there everywhere we see an x, we end up with all of this stuff. Where we had x, we now have I theta. Where we had x squared, we now have I theta squared. Where we had x cubed, we have I theta cubed, and so on and so forth to infinity. I want to rewrite these numerators in a slightly different way just to make things clearer for us. Let's go ahead in each case and distribute the exponents so that, for example, instead of having I theta squared, I can just write that as I squared theta squared. And I'm going to do that on all the other ones so that I end up with this. And I did that so that I have just my plain old powers of I, which I can read off of my little dictionary right here and write them in yet another form. Well, I squared, that's great. I know I squared, of course, is -1 by definition of I. It's the square root of -1, so you square it and I get a -1. So I'm going to turn that into a good old-fashioned negative. And then I've got I cubed. What's that? Oh, I have that over here. I cubed is minus I. So let me go ahead and make that change. I to the 4th, well, that's just 1, so be gone. I to the 5th, we're back up to I. So let's get rid of that exponent. I to the 6th, that's I squared, which of course is -1. So we make that change. And then the last one I have here, I to the 7th, which is I cubed, better known as minus I. And actually, I noticed that since I pulled the I out here and here, I should probably pull it out here too to be neat. That's better. Just to be totally consistent, I'll do that too. All right. So at this point, you can ask, where exactly are you leading me in this dark wood? We started with e raised to an imaginary power, which is strange enough to begin with. And now I'm supposed to get excited about the fact that it's equal to all of this bizarre stuff. I've got infinitely many terms. The terms alternate between real and pure imaginary. Real, imaginary, real, imaginary, real, imaginary, real, imaginary. What's going on there? Well, let's gather up all the real stuff in one package and all the imaginary stuff in another package, just like it was one giant complex number, a plus bi. If we do that, then the real stuff is going to be this stuff, all the even-powered terms. And then I'll gather up all the imaginary stuff, and rather than having a million i's floating around, which sounds like a horror movie, let's pull the one I out in the beginning. So we'll factor the one I out of all the odd terms involving i's. And when we pull the rest of the stuff into those parentheses, we will get all this stuff. This gives us the theta, this gives us theta cubed over 3 factorial, and so on and so forth down to infinity. So now I have this one complex number where both the real and imaginary parts are themselves infinite series. Oh my goodness, what is this stuff in the first term? It is cosine. Yeah, I've got a theta there instead of x, but big deal. It's the same damn thing. So that whole expression is going to be cosine theta. And what's in the other set of parentheses? That is the Taylor series for sine. So the rest of that stuff is sine theta. Look what we have discovered. Forget about this intermediate stuff. E to the I theta. What is it? It is cosine theta plus I sine theta. Let me write that without any of the clutter left over. Remarkable. A connection between the exponential function and sine and cosine. Functions that seem so different from one another. But they are actually connected in a very simple manner, albeit through the complex plane, through complex numbers. It's amazing how frequently that sort of thing happens, where using complex numbers reveals really surprising truths in mathematics. Two last things I'll say about this. One is its name. It's often called Euler's identity, at least in this context. The problem is there's probably 10,000 things in mathematics called Euler's identity. He did so much, but this is one of them. And I want to show you one specific case in this identity. When theta equals pi, this becomes e to the pi I is equal to cosine pi plus I sine pi. Well, cosine pi, that's just -1, and sine pi, that's 0. Push this 1 to the other side, and we get e to the pi I plus 1 is 0. There are some who consider this the most beautiful equation in all of mathematics because it relates the 5 most important constants in math: 0, 1, pi, e, and I in as compact a space as you could possibly hope for, involving the most important and simplest of operations: addition, multiplication, and exponentiation, and with no fat whatsoever. Anyway, I hope you enjoyed that. And this is just one example of how amazing things tend to fall out of Taylor series. But enough of that good stuff. Forget about complex numbers. Let's come home to the basic good old real numbers. Take your favorite Taylor series, which I will declare to be the Taylor series for e to the x, but any other one would do. A Taylor series is, at the end of the day, a function. It's a function in a complicated form, but it's a function. It accepts inputs from a domain, and it produces outputs, and a Taylor series is built up from familiar operations. The only thing that's weird about it is buried in these ... dots at the end. What is going on at infinity? If I think of it just as some function, f of x is this, and I evaluate it at 22, well, in one sense, I know what that means. It means, all right, well, that's 1 plus 22 plus 22 squared over 2 factorial plus, and so on and so forth. But I'm sweeping a lot under the rug in that and so on and so forth. If I stopped after 5 terms, well, sure, it's just ordinary arithmetic. If I stopped after 5 million terms, it would just be ordinary arithmetic. But I'm saying don't stop. Go to infinity. What does that really mean? Forget about the fact even that this is a Taylor series. Forget about the fact that it's a function. Just think about this idea. We are adding up infinitely many numbers. Each one of these is a perfectly ordinary number. How can we add infinitely many of them? What does that even mean? So what we need to do is put all the Taylor stuff up on the shelf for a little while. We will get back to it and just concentrate on what we mean by an infinite series of constants. Most of them will not have this weird form that comes out of Taylor series, but we'll build back up to them. We'll start with much more humble problems, like, say, making sense of this infinite series, or even one you met in elementary school, this series. Now you may be thinking, what the hell kind of elementary school did you think I went to that we talked about infinite series? Well, you didn't talk about them explicitly. But believe me, you saw this, because if we wanted to get a sense for what this was, what would you do? Well, you'd start at the first term, and you would make a running sum as you went. You'd keep a running total. And what would you do? You say, all right, well, that's 0.3. And then I add on 0.03. So that's 0.33. Then I add on that. Oh, so that's 0.333. And I add on that. That's 0.3333. And the next one, that'll give me 0.33333, and then I'll have 6 threes and 7 threes, and so on and so forth. Now, where's that all headed? Well, after 100 terms like this, what'll you be at? 0.333333333 100 times. After 1,000,000 terms, you've got 0.333333333. That running total of yours is clearly getting closer and closer and closer to something. It's not going to suddenly jump out and the running total will hit 7. It's always just 0.33333, and you know where that is all headed. If you have 0.3 repeated, as you might have said in elementary school, that is just another name for 1/3. So yes, you did actually meet an infinite series in elementary school. You didn't write it like that. You wrote it like that, but it's still an infinite series. That's just positional notation. 3/10 plus 3/100 plus 3/1000 plus 3/10,000 plus 300,000 and so on to infinity. Add it all up and you get 1/3. And that is the intuitive idea behind an infinite series. You start at the first term and just keep adding terms, keeping a running total as you go, and that running total might get closer and closer and closer to some particular value, like the last one did, was getting closer and closer and closer to 1/3, in which case we say that the infinite series converges, or the running total might not get closer and closer and closer to something, in which case we say that the series diverges. So here's a simple intuitive example of a divergent series. The sum of all the natural numbers. All the natural numbers. If we start at 1 and start adding them up and keeping a running total as we go, well, we get, let's see, 1 and 2 is 3, and 3 is 6, and 4 is 10, and 5 is 15, and 6 is 21, and so on and so forth. Is that getting closer and closer and closer to some value as we go? No, of course it isn't. That running total is just blowing up to infinity. Because the running total isn't getting closer and closer and closer to something, we say that this series diverges, or that this is a divergent series. And one of the things we will be spending a lot of time on in the next few weeks is trying to decide, when we're given some particular numerical series, trying to determine whether it converges or diverges. We usually won't even be able to tell, even if it converges. We usually won't even be able to tell the value to which it converges. But at least we'll be able to say, this converges. This is something sensible that we can talk about. But a divergent series is pretty much useless. It isn't anything. It doesn't add up to anything. I want to give you one more intuitive example of a divergent series. They don't all have to blow up to infinity like this one. Consider this series right here. Does it converge? Does it diverge? Well, suppose we start at the first term and add up and keep a running tab on what the total is. The first term is 3. Then we subtract 2. Okay, that brings us down to 1. Oh, then we have 2, so our running total is up to 3. Oh, we're back down to 1. Oh, now we're up to 3, down to 1, up to 3, down to 1, so on and so forth. The pattern is clear, but the running total is just hopping back and forth between 3 and 1. It's not as if we went out a million terms in the series and we said, okay, now I see, it's getting closer and closer. No, it would just be the same thing, just bouncing back and forth between 3 and 1 is what our running total would be doing. So that series also diverges. Are you getting an intuitive feel for this? I hope so. We keep a running total. If that's getting closer and closer to something, it converges. If not, it diverges. Some divergent series blow up to infinity or go to minus infinity. Is that blowing down to minus infinity? Some of them just have a running total that bobbles back and forth like this. We don't really care. If it diverges, it diverges. It's useless to us. Let's do one last intuitive example before we define these things a little more formally. I have left this thing on the bottom tantalizingly the whole time. I have not forgotten it. Let's talk about it. There are a few ways to think about this. Straight arithmetic, we could say, all right, let's see. I've got a half, and then I add a quarter. Well, what's that? That's 3/4. And then I add an eighth. That's 7/8. And then I add a 16th. That's 15/16. And then I have to go, and it's a little ugly, but you might see a pattern there. But a nicer way is to think about it geometrically on the number line. Here's 0, and here's 1 for scale. First thing we do is we add a half. So that takes us from 0 to 1/2. To that, we add a quarter. So I have to go out another quarter. And that takes me here. So I've added on a quarter, which of course gets me to 3/4. That took me halfway, since a quarter is a half of a half. Well, now I'm adding an eighth, which is half of the quarter that's left. So now I add on an eighth, and it takes me right here. That's 7/8, but, well, I guess I am going to write down. Then I add on a 16th. Well, a 16th is half of the eighth that remains on our journey to 1. That's an extra 16th I've added. That's going to take me right here. Then what happens? I add on a 32nd, which is half of the way again, and a 64th, which is half the way again. And I am running up against the limits of what I can draw, but you get the idea. I keep adding on smaller and smaller things, each of which takes me halfway to this wall at 1. And some of you may recognize hints of Zeno's paradox in this, if you have met that. But anyway, our running total, which is down here, 1/2, 3/4, 7/8, my running total is just these points right here. That's my running total. Are those getting closer and closer to something? Yes, of course, my running total is approaching 1. After any finite number, it will still fall short of 1. If I add up 1 trillion of these, I'll still be ever so slightly short of 1. But if I add up all of them, we say that the series converges to 1, because that is the number that the running total is approaching. So this is a convergent series, and we say it converges to 1. Now that you have the intuitive idea of what is meant by an infinite series of constants, now that you have that idea with its built-in sense of a limit, let's make that limit explicit and write down a formal definition for an infinite series, and introduce some terminology and all that sort of thing. So, suppose we have a series, and here I need to write a symbol for a series. In the same way that you have seen sentences that begin, suppose we have a function f, or suppose we have a vector v, or suppose we have an equation y equals f of x, or whatnot. Suppose we have a series, and I will write it this way with sigma notation, where the ith term is denoted a sub I, and I runs from 1 to infinity. If you don't like sigma notation, well, you do need to get used to it, but you can always write it out. I actually like writing things out more often than not, so I'll go ahead and do that here too, like so. Anyway, if you have any old series, then what I was calling a running total before is officially called a partial sum. The idea is you're not summing all the way up to infinity, you're just summing part of the series. In particular, given a series like this, its nth partial sum, which we usually denote s sub n, is defined as the sum of its first n terms. So it's just an ordinary finite sum. Or in symbols, Sn, the nth partial sum, is the sum of the first n terms, as I runs from 1 to n. And here too, if you like, you could always write that out, like so, stopping at a sub n, unlike the full sum, the infinite series, which just goes on forever. So the first partial sum is just the first term of the series. The 10th partial sum is the sum of the first 10 terms of the series, and so on and so forth. That being so, to connect this to our intuitive ideas from before, the convergence status of a series, that is, whether the series converges or diverges, depends on the limit of Sn, the limit of the nth partial sum, as n goes to infinity. So, if Sn, the nth partial sum, approaches a specific value as n goes to infinity, we say that the series converges to that value. And on the other hand, if not, if this doesn't happen, then we say that the series diverges. And that's that. Now you know the official language as far as convergence and divergence is concerned. A convergent series is one whose nth partial sum goes to some particular value in the limit. Very intuitive, and I think even elegant in its way. There's no reason why the index on your series has to begin at 1. I'll often start it at 0, a sub 0, a sub 1, etc. You just use whatever suits the occasion. You could start it at 17 if you want and go from 17 to infinity. It wouldn't change the fact that it was an infinite series. As we will talk about more and more, all the magic in the infinite series is in the infinite part, in the tail of the series. The early stuff affects the actual value of the sum, the value to which the series converges, but it actually has no effect at all on whether or not the series does converge. All that action takes place out here in the infinite tail. But that's something we'll be discussing more about and you'll be reading more about as the course develops. And now that you know the official definition of a series, we can start getting more specific. There are different species of series out there. We will meet some of them in this course, and the simplest, the nicest, the best behaved are the ones called geometric series. We're finally getting particular. A geometric series is a series with a particular form. This one, you start at some number a, and then the next term is r times that number, where r is some other number, and then the one after that is r times the previous term, and the one after that is r times the previous term, and r times the previous term, and so on. And so on is a common phrase when you're talking about infinity. And that is all that is meant by a geometric series. The definition is simple. And now we should look at some specific concrete examples of geometric series, particularly now that I have escaped into another room where the air conditioning is not so loud. First example. This series, 2 plus 4/3 plus 8/9 plus 16/27 plus so on and so forth. Is this geometric? Well, does it have this form? It does. It's got a first term. Every series does. That's no surprise. But the important thing is that every successive term we obtain by multiplying the previous one by the same thing. If I start with 2 and multiply by 2/3, I get 4/3. Multiply by 2/3 again to go from 4/3 to 8/9. Multiply 8/9 by 2/3 and we get 16/27. And the ellipses here mean the pattern continues. Thus, this guy is indeed a geometric series with a equals 2 and r equals 2/3. Remember, a just indicates the first term in the series, first letter in the alphabet, and r represents this common multiple. You multiply each term by 2/3 to get the next term. You might ask, well, why don't you call it m then? Well, for two reasons. One, everybody calls it r, so I will call it r as well. But also, if you shift your perspective, you can think of any multiplier as a ratio. Sure, I multiply by 2/3 to go from one term to the next, but that's equivalent to saying I divide by 2/3 to go from any term to its predecessor. That's why we use r here. R for ratio, even if we tend to think about it as a multiplier.
And now for another example.
-2 plus 10 minus 50 plus 250. You get the idea. Is it geometric? Well, is every term the same multiple of its predecessor? Sure is. To get from -2 to 10, you multiply by -5, which is the same way you get from 10 to -50, or from -50 to 250. So yes, this series is indeed geometric, with a, first term, -2, and r, that common ratio or multiplier, of -5. Okay, so it's not hard to spot geometric series. We like them because it turns out that the convergence status of a geometric series, and again, by convergence status, I just mean, does it converge or does it diverge? The convergence status of a geometric series is determined entirely by the value of r. You give me a geometric series, once I know the value of r, I can tell you whether or not that series converges or diverges. And it's actually pretty easy to see why knowing r is enough to tell you whether or not the series converges or diverges. Let's run through the various possibilities, and then we'll summarize it all very neatly. Let's start with a trivial case. Suppose r is 1. Well, the series would be very boring in that case, because we'd start wherever we started, a, and then we multiply by 1 to get the next term, and multiply by 1 to get the next one, and keep multiplying by 1. And so our series would be a plus a plus a plus a plus a. Well, ignoring the silly case where a is 0, and we have 0 plus 0 plus 0, we can ignore that because we wouldn't even be talking about such a trivial series. But for any other a, it's obvious that the series would diverge, because our running total, our partial sums, do not settle down to any particular value. They just keep getting bigger and bigger and bigger and bigger. At least in absolute value, a could be a negative number. Thus, this series diverges. What about if r is greater than 1? That's a little more interesting. In that case, our series takes the usual form, but think about the successive terms. Each term, if r is greater than 1, is bigger than the one that came before. Like if r is 1.5, then this term is 50% bigger than that one, and this term is 50% bigger than that one, and so on and so forth. If the terms keep getting bigger, they're just greedily shoveling more into the total. So in this case, where r is greater than 1, we also know that the series diverges. What, does the geometric series always diverge? No, of course not. And for the very simplest example, but one that's, again, too silly almost even to mention, is this. Suppose r is 0. Then what does our series look like? Well, we have our first term a, and then we multiply that by 0, and then we get another 0, and we keep multiplying by 0, so we just get zeros all the way. Well, that's an extremely stupid series, because all those zeros amount to nothing. And obviously, the series converges. In fact, it adds up to a, because that's the only non-zero term. But it's nice to see at least one example so far of a convergent geometric series. It might be worthwhile making a little picture. Let's just call this the r-axis. We know that at 0, we get convergence. If r is 0 in a geometric series, it converges. If r is 1, we know that it diverges, which I'll put in red. And we know that if r is anything greater than 1, the series is going to diverge. Let's look at a few other specific cases. Suppose r is -1. Then what would the series look like? Well, you'd have your first term a, then you multiply by -1 to get your next term, so minus a. Then you multiply by -1 to get plus a, minus a, plus a, minus a, plus, and so on and so forth. But we saw an example like that when we were just speaking intuitively. Clearly, that one diverges. Because after all, think about the partial sums. They do not settle down to any particular value. They just keep flip-flopping between a and 0. Our first partial sum is a, our second partial sum is 0, our third is a, our fourth is 0, our fifth is a, our sixth is 0, and so on and so forth all the way to infinity. So if I go up here on my chart, I have another red spot. Okay, suppose r is less than -1. We've got some r value back here. What can we say about our geometric series in that case? It might help to think of a concrete example here, and if you see one, you'll see why this applies to any such case. Let's just say we started at 3, and let's say our r value is minus 1.2. So then the next term would be minus 3 times minus 1.2 squared, and then we get 3 and minus 1.2 cubed, and so on and so forth. Well, this is very much like the case where r was greater than +1, in that each successive term is getting bigger, at least in absolute value. The signs keep switching. This one's going to be negative, and this one's going to be positive, and this one's going to be negative, and so on and so forth, which means that in our running total, our partial sums, we're going to be adding a number and then subtracting something that's bigger, and then adding something that's bigger, and then subtracting something that's bigger. So we're going to be jumping around the number line like crazy. If this is 0 and we start at 3, so that would be our first partial sum, we go from 0 to 3, then we're going to subtract something off that was bigger than the previous step. So we'll end up somewhere down here at this point, which will be our second partial sum. Then we're going to add something on that was bigger than the previous step. So we'll end up somewhere over here for our third partial sum. Then we're going to subtract something off that was bigger than that step. So we're going to end up somewhere over here at the fourth partial sum. And you can see what's going to happen. These partial sums are going to be hopping back and forth on the number line, bigger and bigger and bigger and bigger without bound, because if you take any number that is greater than 1 and keep raising it to higher and higher powers, its magnitude grows without bound. They are not settling down to any particular value. And there's nothing special about minus 1.2. The same would be true of minus 1.001 or minus 100. In a situation like this, the geometric series is going to diverge. So if I go back to my drawing up here, I can fill all this in as well. And now we've taken care of what is, in some sense, the uninteresting aspects of geometric series. But it's good. Just by working with some examples and thinking about it, we're getting a feel for how it works. And you want to have an intuition. You don't want to end up with just a formula at the end where you say, in this circumstance, this happens, and in this circumstance, this happens, and I've memorized it, but I have no idea why. You want to know why things happen. And make sure you start thinking about such things early in your studies of series. It's a potentially tricky subject. Anyway, now we can turn our attention to the interesting region when r is a number between -1 and 1, when r's absolute value is less than 1. We actually saw an example of this earlier. We looked at the series half plus a quarter plus an eighth plus a 16th and all of that. And on purely intuitive grounds, we said that this one was going to converge to 1. That was the one where we were kept going halfway to the wall. But I mention it here because this is a geometric series. We keep multiplying by a half to get to the next term. This is a geometric series where a is a half and also r is a half. And that one converged. Does that mean every geometric series whose r value is between -1 and 1 converges? Well, no. The fact that this happens in this case doesn't mean it necessarily happens for all of them. But on the other hand, it is a possibility. We need to investigate more closely. In fact, we'll get the most insight if we back up for a second and forget about the fact that we're ultimately interested in what happens in here. Let's consider any geometric series whatsoever. One interesting thing about a geometric series is that you can come up with an explicit formula for the nth partial sum by a very clever argument. I think you'll like this one. Let's find a closed formula for the nth partial sum of a geometric series, and here is a general expression for any geometric series. A couple of things I should mention here. First of all, does this expression really capture every geometric series? Sure it does. Just imagine writing this out. Here I've started my series at 0 because then I can say the first term in the series is a times r raised to the 0 power. But r raised to the 0 power is 1, so the first term would indeed be a like it's supposed to be. Then when I is 1, I get ar. Then I get ar squared, ar cubed, etc., etc. So yes, this will capture any geometric series. Okay, we know what's meant by the nth partial sum, but what do I mean by a closed formula? I mean something that doesn't have ellipses anywhere in it, or a giant summation, even if it's finite, something that I can actually evaluate. Because I can write down a formula for the nth partial sum of this geometric series very easily. I mean, we could say that S sub n, well, that's a plus ar squared plus ... all the way down to a times r to the n minus 1 power. Ah, n minus 1? Isn't that supposed to be n? I hear you cry. Nope, it's n minus 1. This is one of those places where we have to be a little careful. The first term involves r to the 0. The second term involves r to the 1. The third involves r to the 2. So the nth term, which is where I stop summing, will involve r to the n minus 1. So this is a perfectly good formula for the nth partial sum, but it's not a closed formula. It's not something I can really evaluate. I mean, suppose I say, all right, here's a series. Give me the 100th partial sum. All this is telling me is, well, first you take the first one, and then the second one, and then the third one, and all the way up to the 100th, and add them up. Yeah, I know that, but I'm looking for something that doesn't involve 100 additions. For a general series, this is all you can say. But for this very special species of geometric series, we can actually come up with a closed formula. I'm going to show you how it works. I'm going to start with this expression, and we're going to play some very clever algebra games. I'm going to multiply both sides by r. When I do that, I get rsn on the left side. What do I get on the right-hand side? When I multiply r by a, I get ar. Rather than writing that here, I'm going to write it under here. When I multiply that r by ar, I get ar squared. Well, I'm going to write it underneath that other ar squared, and so on and so forth. And so I'll end up with an expression like this. This one actually goes to ar to the nth, because when I multiply r by this last term, well, I get that. Well, the little algebra student within you should be crying out, ooh, I see what I can do here. Look at all this massive cancellation we're going to get if we subtract the lower equation from the top one. And that little algebraist within you is correct. If I subtract the lower from the upper equation, on the left-hand side, I get 1 minus r times Sn. And on the right-hand side, yes, I get tons of cancellation. All that survives is that initial a. All that stuff is gone, and this guy, which gets subtracted, but he doesn't have a mate over here, so he gets subtracted down here as well, ar to the n. And remember our goal, find a closed formula for the nth partial sum. Well, here's the nth partial sum. I can just solve for it now. Solving for S sub n, we get this expression, which will look nicer if I factor out the common a upstairs, giving me this. Neat. It's a closed formula for the nth partial sum of a geometric series. This isn't something you need to memorize or anything like that, because it's easy to come up with, and you get to enjoy that little argument, but it's nice. Now, if you have a geometric series and someone says, I want the 100th partial sum, you don't have to start adding up the actual 100 numbers. For example, let's consider the series 3 plus 6/5 plus 12 25ths plus 24 over 125, and so on and so forth. And suppose I ask you to find the 100th partial sum. Well, you don't want to sit there like a dope and say, well, 3 plus 6/5, that's 15/5, that's 21/5, and then I have to add. You'll be there all day. You've just derived this very nice formula. Let's use it. Well, of course, before we use it, we have to make sure it applies. Is this, in fact, a geometric series? Yes, it is, because to get from any term to the next, we're multiplying by 2/5, as you no doubt discerned already. So we could say, well, the 100th partial sum, what's that? I'll just use my formula. A is the first term, that's 3. 1 minus r is 2/5. I'm raising it to the 100th power, and I'm dividing by 1 minus the ratio, 2/5. Well, 1 minus 2/5 is 3/5, and dividing by 3/5 is like multiplying by 5/3, so that's going to be 5 times 1 minus 2/5 to the 100th, whatever that is. But that's it. That's the partial sum. So the formula is really easy to use. There's something I want you to notice about this before we get rid of it. 2/5 to the 100th power. Forget about the actual value of 2/5 to the 100th power. That's not very interesting. But just think more qualitatively. Is this a big number, a small number? What is it? It's a tiny number. What is it? It's 2/5 of 2/5 of 2/5 of 2/5 of 2/5 of 2/5 100 times. It's practically nothing. If you start with 2/5 of a pie and then take 2/5 of that and 2/5 of that and 2/5 of that and 2/5 of that, you're not even going to have a molecule of it left. So this thing is damn close to 0, which means that all this stuff in parentheses is very close to 1, which means that our running total after 100 terms is very close to 5, which means that it's a pretty good guess that this geometric series is going to sum up to 5. And indeed it will. Let's take the insight we gleaned here and see how it plays out in the abstract, so that we're not just thinking about this one concrete case, but any old geometric series. We've solved our problem. We have our closed formula for the nth partial sum, but the reason we care about the nth partial sum is because we know that when we take the limit of the nth partial sum, we get the sum of the series, provided that limit actually exists. So let's do it. Note that if the absolute value of r is less than 1, that's that case we're looking for here, where r is between -1 and 1. Then the limit of the nth partial sum as n goes to infinity is the limit of this stuff, the formula we just discovered, as n goes to infinity. What's that going to look like? Well, a is just a constant, so the limit doesn't do anything to that. 1 minus r is just a constant. 1 is just a constant. But if r is a number whose absolute value is less than 1, that means that as we take higher and higher powers of it, it shrinks away. If r is 0.32, then we're taking 32% of 32% of 32% of 32%. Even if r is negative 0.03, then we're taking 3% of 3% of 3%. Yeah, the sign keeps flipping back and forward, but the magnitude of the thing is going to 0. Accordingly, r to the n is vanishing. It's going to 0 in the limit, which means that this limit is just going to be a times 1 minus this thing that vanishes, so times 1, so I don't need to write anything up there, over 1 minus r. Hallelujah! What have we just deduced? We have deduced that if r, that ratio that governs a geometric series, lies between -1 and 1, then the limit of its nth partial sum is a specific number, a over 1 minus r, first term over 1 minus that common ratio. So that means that the series, the geometric series, with absolute value of r less than 1, converges. And not only converges to something we know. We have a formula for the actual sum that the thing goes to. Good. So if I was to fill out my picture, now I know that we get convergence for any value of r between -1 and 1. Let's summarize what we have discovered. Given any old geometric series, that's the general form for a geometric series, such a series converges if and only if r lies in this region. That is, if and only if the absolute value of r is less than 1. Moreover, if it converges to a over 1 minus r. This famous formula you should commit to memory. Let's put it to use in an example or two just to see how it works. Oh, let's go back to that one that we looked at a moment ago, this geometric series. Once we recognize that this is a geometric series, we're multiplying by 2/5 every time, we just ask ourselves, what do I know about r? Is its absolute value less than 1? Sure is, it's 2/5. That means it converges. Not only do I know it converges, I know what it converges to. This thing is going to be equal to, what's the formula? A over 1 minus r. Kind of looks like air like that. A, that's the first term. Oh, well, that's easy. That's 3. 1 minus r. That's 1 minus 2/5. But 1 minus 2/5 is 3/5. And I do the division, and I get 15 over 3, which is 5, just like I said it looked like it was going to be. Ha-ha! We win! And maybe just to get in the habit of justifying what we're doing, I'm going to note that this equality right here is justified because we are working with a geometric series. We're going to have a lot of problems where you'll be given a series and you have to decide whether it converges or not, and you'll need to note what kind of series you're working with, what kind of tests we're using, so on and so forth. So it's good to get in that habit. All right, let's do one more example. 8 minus 8/3 plus 8/9 plus 8/27. What can we say about this series? Is it geometric? Yes, it is. To get from each term to the next, we are multiplying by -1/3. Does it converge? Yes, it does, because a geometric series converges if r is anything between -1 and 1. -1/3 certainly qualifies. And in fact, we know what it converges to. It's this usual formula with its counterclockwise air. You do not have to use my stupid mnemonic. A, that's 8. 1 minus r. The r is -1/3. Careful not to omit that minus. It is crucial. Well, that's 8 over 4/3. Dividing by 4/3 is the same as multiplying by 3/4. So that's 24 over 4, which is better known as 6. So this series, which hops back and forth between negative and positive terms, but the terms are getting smaller and smaller, converges on 6. And we are done. All right, one last. This thing, is it geometric? Yes, because every time we are multiplying by 1.01 to get from one term to the next. Does that mean I can go and plug things into this formula? No! It doesn't apply. Even though this is a geometric series, it is a divergent geometric series because r is greater than 1. We only get convergence if r is between -1 and 1. So this series diverges. It is no good at all. All right, I think we've said just about everything we can say about geometric series. They show up in all sorts of interesting places. They turn up in probability, they turn up in fractal geometry, but I want to end by connecting them back to something we've already talked about in this class. And I want to tie things back to something we mentioned in the beginning of this very video. Taylor series, and one particular Taylor series. One of the 4 you should have memorized is the one for 1 over 1 minus x. That's the really simple Taylor series where every coefficient is 1. Hey, wait a second. Look at this Taylor series. There's something interesting about it. By God, it's geometric. To get from any term to its successor, we multiply by x. Holy moly! Well, if this thing is a geometric series, that means it converges if and only if r, which is x, has an absolute value of less than 1. And in fact, it converges to a over 1 minus r. Well, what's the first term? 1. 1 minus r. What's r? That's x. Oh, that's this. We already see that it's equal to that thing. And now we got it without doing any derivatives or anything like that. Much more interestingly, this condition here, that it converges if and only if the absolute value of x is less than 1, that explains those tripwires in that picture we looked at before. That tells us why this Taylor expansion is equal to this function only under certain conditions, only when x lies between -1 and 1. So here, geometric series have given us an insight into a weird phenomenon that we saw with a particular Taylor series, and prior to that with particular Taylor polynomials. All this stuff is interrelated, and that, of course, is half the fun and fascination of mathematics. All right, geometric series are great. Don't let them spoil you. The nice thing about geometric series is that it's a piece of cake to tell whether they converge or not. All we have to do is look at r, and not only that, if it converges, we know what a geometric series converges to. That is a real treat that's not going to be typical with most series. Usually we'll have to rest content saying, I know such and such series converges, I do not know the exact value to which it converges. All right, that wraps up another longish video. Maybe these all will be long, I don't know. We'll see. But I will see you next time, or rather, you will see me, or rather, you will listen to me and see my handwriting when we talk about the infamous harmonic series. Goodbye.